Hi, my name is Georgia, and I'm a fourth-year biomedical engineering student at the University of Colorado Boulder. In today's lesson, we're going over the water cycle and types of data displayed in hydrographs. Afterwards, we'll discuss how to use conservation of mass to calculate the regional water balance equation and estimate the amount of runoff leaving a watershed. Let's dive in. Have you ever heard of the term hydrology? What do you think it means? Let's break it down. Hydro is a root meaning water, and ology means study of. Hydrology, therefore, is the study of the distribution and quality of water on Earth. One of the most important concepts in hydrology is the water cycle, which describes how water moves through Earth's systems. Think about a single drop of water in your backyard. Where might it go over time? Maybe it falls as rain and flows into a nearby stream. Perhaps it soaks into the ground and becomes groundwater. It could evaporate into the atmosphere, form a cloud, and later fall back to Earth as precipitation somewhere else. This continuous movement of water through the atmosphere, land, and oceans is called the water cycle. As we look at this diagram, notice the different ways water moves throughout the system. Water falls from the atmosphere as precipitation, returns to the atmosphere through evaporation, and travels across the land as runoff or below the surface as groundwater. Together, these processes keep water moving through Earth's interconnected systems. The major components of the water cycle include precipitation, evaporation, runoff, and groundwater movement. These processes move water between Earth's main water storages, the atmosphere, land, and oceans. Hydrology is a huge factor when it comes to discussing watersheds. A watershed is an area of land where all water drains to a common river, stream, lake, or outlet point. For instance, if we have a bunch of different sources of runoff all leading to the same river, which leads to the same ocean, all of that land is included in the watershed. Water within a watershed can exist as precipitation, surface water, or groundwater, and it can move through the system by processes like evaporation. Water within a watershed can be stored in several places. These are called storages. Assuming our watershed is a closed system, we can apply the principle of conservation of mass to our watershed and come up with a balance equation that tracks how much water is in each of these storages. What is conservation of mass? It's exactly what it sounds like. Since matter can neither be created nor destroyed, mass is conserved over time for any closed system. Assuming that the amount of water on Earth doesn't change, we can consider the water cycle a closed system. Therefore, we can use the conservation of mass equation to calculate how much water is stored in different places. The equation for conservation of mass is inputs minus outputs equals storage. What are the inputs of water in our watershed? Precipitation and groundwater flowing in account for the water coming from another storage. What about the outputs? Runoff, evaporation, and groundwater flowing out account for the water going to another storage. Substitute these variables into the equation and we will get a result specifically tailored to our watershed system. Precipitation plus groundwater flowing in minus groundwater flowing out plus evaporation plus runoff equals storage. To simplify our equation, we can assume that there is no net storage in the system over very long periods of time. Our equation comes out to runoff equals precipitation minus evaporation. After it rains, water can infiltrate into the ground and replenish our groundwater supply, or it can evaporate, returning to the atmosphere. Some water may flow into rivers and streams, which lead into oceans or reservoirs. Surface water is referred to as runoff because it runs off the land. Runoff flows across the land surface and often enters streams and rivers before eventually reaching larger bodies of water. Why is runoff important to a community? Runoff can become a source of drinking water or irrigation. Why is runoff important to plants and animals? It keeps them alive and healthy, and it provides habitat for aquatic freshwater organisms. Why would estimating the amount of runoff be important for engineers? This information can be helpful for flood management, hydropower applications such as hydroelectric dams, and water resource and supply management. Consider an environment where it rains a lot. If the amount of runoff is too much for a riverbed to carry, then water can rise up over the riverbanks and flood the surrounding area. In order to prevent damage to infrastructure, engineers need to analyze the behavior of the environment's water systems. We can visualize runoff by using hydrographs. On a hydrograph, time is plotted on the x-axis, and stream flow is plotted on the y-axis. Hydrographs show how runoff changes over time. Take a look at the event hydrograph and compare it to the annual hydrograph. An event hydrograph shows stream flow during a single storm event like a hurricane, while an annual hydrograph plots stream flow over the course of a year or multiple years. The peaks on a hydrograph represent time when stream flow is highest, often following storms or seasonal snowmelt. Engineers must be able to understand, calculate, and graph runoff for all sorts of reasons. Flood control, water supply management, designing and building dams, recreational planning like golf courses or beach clubs, and statistics concerning future flood scenarios are key skills for civil engineers involved in modeling hydrological processes and studying water resource management. Anytime a neighborhood, road, or building is constructed, engineers must assess how rainfall and runoff will move through the surrounding area. If a community wants a new soccer field, engineers must use hydrological data to find the best place to put it. When a hurricane is expected to hit a seaside town, engineers can assess how much damage there will be and how much money and resources the town may need to rebuild. From the beginning of civilization, humans have studied the behavior of water all over the world in order to build and sustain our communities. We learned early on how to take advantage of runoff to power our civilizations, grow our farms, and supply drinking water to our populations. Our knowledge of rising water levels and floods allowed us to plan and design infrastructure around these events. Think about where you live. How often does it rain or flood? Look for elements of infrastructure in your neighborhood that are built to accommodate this, such as drainage systems or man-made reservoirs. If you live in a drier environment, you may find features that try to amplify water levels instead of reducing them. I hope this lesson gave you an understanding of how important our knowledge of hydrology is and what can be done with it. Thanks for watching, and we'll see you in the next video. Bye! Check out the full lesson on the Teach Engineering website. Then, put your knowledge to the test with our associated activities: flood analysis, floodplain modeling, and protecting our city with levees.